Okay, first of all, thank you very much for the organizers for inviting me here and giving me this opportunity to present my work. So today I'll talk about the constraints, some new constraints on Kahler moduli space of 6-dimensional n=1 Supergravity series. And this talk is actually based on my paper last month with Kahler. So as we all know, the Supergravity series is a very interesting subject, particularly in the context of the Swampland program. So we can engineer many of these theories using the F theory or string theory various background. And from the bottom-up perspective, these theories are strongly constrained by anomalies, so which makes this program much more interesting. Actually, this also allows some people to carry out classification programs, as Yuta already explained in his talk on Mondays. So actually, he explained his remarkable achievement along this direction of classifications. We know that not all the anomaly-free supergravity theories in 6 dimensions can consistently couple to quantum gravity. We can see it, for example, by using some non-perturbative constraint coming from the string probes. So actually, using the consistency of the current algebra living on the 2D CFT on strings, we can try to find some bound on the rank of gauge algebra, which you cannot see from the perturbative perspective. Or you can also find some minor constraint on the metal representations. However, these non-perturbative constraints are still not enough to provide the full constraint or fully fill out the gap between the 6D quantum gravity landscape and the Swampland, or the space of the anomaly-free 6D supergravity series. So we need more constraint. In particular, these string probe constraint cannot provide extra constraint when the rank of the gauge group in 6D supergravity series is very small, such as for U1 gauge series or SU2 gauge series. And these constraints cannot give us a new constraint usually. So we have to find more constraints. So today I'll talk about some attempt to find the new constraint of 6D supergravity series based on the following aspect of the moduli space of this series. So for example, I'll consider 5D compactification of this theory, and also Higgs branch RG probes, and unitarity of BPS strings, and even the classification of the 5D SCFTs. So I know all these subjects are very interesting subjects by themselves. And as I'll show you, when we combine all of them together, we can uncover more constraints and also make very concrete prediction for the 6D quantum gravity, in particular when the rank of the gauge group is very small. So let me start with a brief introduction to 6D10 supergravity series. But fortunately, Yuta already gave a brief introduction, so I can skip this part. But let me just explain my notations. So here, T and V and H in my talk denote the number of tensor, vector, and hypermultiplets. And this is the anomaly cancellation condition using the Green's branch mechanism. Here, the anomaly coefficient in my talk, I denoted them by A and BIs. Okay, let's consider circle compactification of the 6D supergravity theory. Then the 6D gravity multiplet reduced in 5 dimensions, gravity multiplet together with the vector multiplet. Here, the vector field in this additional vector multiplet from the 6D gravity multiplet come from the circle compactification of the two-form, self-dual two-form gauge field in the gravity multiplet. And 6D tensor and vector multiplet, they both reduce to the vector multiplet, and hypermultiplet in 6D becomes a hypermultiplet in 5 dimensions. And 5D supergravity theory has a Coulomb branch, which is parameterized by the scalar field in these vector multiplets. And actually, if this 5D theory comes from the 6D supergravity theory, then there is a very systematic way to compute the low energy effective Chern-Simons Lagrangian, which actually characterize the properties of the 5D supergravity theory. So this computation has been carried out in various papers. So for example, so we have to take into account the Kahler-1 contribution to the effective Chern-Simons Lagrangian, which is done in this paper, and this is the vector. And also we have the classical Green-Schwarz contribution, which looks like this. And also zero mode contribution is this. So for the known 60 data, merciless metal content, you can systematically compute the effective Chern-Simons Lagrangian in 5D computification. So here A0 corresponds to the gravity photon, and F alpha is the vector field coming from the 60 tensor multiplet, and also AI comes from the 60 vector. So today I focus on the analysis of 5D rank 1 supergravity theory. So for the generic rank 1 supergravity theory, the cubic potential, which we can use to extract the effective Chern-Simons Lagrangian, can be generically written in this way because it's at most cubic. We have only 4 integral coefficients. These 4 integral coefficients characterize the generic rank 1 5D Coulomb branch of the supergravity theory. So it's rank 1. So overall scaling of this pre-potential is controlled by hypermultiplet. So we have two parameters T1 and T2 for writing down the pre-potential. And these two parameters are called Kahler congelators. And the Kahler cone, so here I use the word Kahler cone to denote the Coulomb branch, more precisely the physical region of the Coulomb branch, whose boundary is defined as where T1 vanishes or T2 vanishes, we have massless BPS particle states. Within Coulomb branch, these 4 Chern-Simons coefficients are strongly constrained by unitarity. For example, the monopole string tension must be positive in the Coulomb branch. It actually provides a constraint that these 4 coefficients must be non-negative. And if we have geometric realization of this 5D theory, then this condition is kind of trivial. But here, I will discuss most constraint beyond the geometric consideration or without assuming any specific UV completions. So I have to prove all the conditions from the bottom-up approach. So monopole string tension gives this condition, and metric on the Coulomb branch also need to be positive, and they provide these 2 conditions, which I will denote as delta 1 and delta 2 conditions. So there are many conditions among these 4 integral coefficients. Okay. I will use these conditions later to constrain the 60 supergravity theory. Oh, because of the quantization of the Chern-Simons terms under the gauge transformation. Okay, actually, so as a side remark, this same condition can be actually derived from the unitarity of the word CFT in the 5D, okay, monopole string. And from this coefficient, we can extract the behavior of the physics at the boundary. So for example, let's consider the boundary when T2 vanishes. And we have 4 types of boundary physics. Firstly, if C1, C2 vanishes, then as you see, as we approach boundary, the pre-potential scales as scales with T square. In this case, actually, the boundary behavior has been extensively explored in many papers, and this boundary corresponded to the emergent string limit with the light string oscillator mode. And in the second case, if C1 vanishes but C2 positive, then the pre-potential vanishes with the linear in T. And in this case, we have light KK mode. So this corresponds to the decompactification limit back to 6 dimensions. Okay? And these 2 boundaries correspond to the infinite distance limit in the moduli space. We have a third case when delta 1 vanishes, but C1 is positive. In this case, because C1 is positive, so when we send the T to 0, this pre-potential remains finite. It simply means that this boundary is at the finite distance in the moduli space. In this case, actually, you can compute the metric on the Coulomb branch, and metric degenerate, and it means we have the gauge coupling which diverges at the boundary. That signals the emergence of the CFT fixed point at the boundary. Okay, so third case corresponded to the CFT fixed point. And the last case, we have the finite depth. Again, it signals that that is located at the finite distance in the moduli space. And in this case, we have either fluff transition or bioreflection or both. Okay? So by knowing the coefficient, you can actually extract many information about the boundaries on the Coulomb branch. And in particular, we will use these third boundary conditions on the Coulomb branch to exclude some of the interesting Schick dispergravity theories. So let's come back to Schick dimensions. So let's first consider the simplest Schick dispergravity theory with a tensor and vector multiplets. And this theory can actually be realized in F theory compacted by the elliptic P2. And using the formula I have shown, you can compute the effective prepotential in 5 dimensions in this way. So this is, in 5 dimensions, you have the rank 1 5 dispergravity theory with this prepotential. And this so Coulomb branch has 2 boundaries. One is where T0 vanishes, and the other boundary is where T1 vanishes. And actually, at the boundary, in the first boundary, if you look at this one, and using the previous slide argument here, you can identify the first boundary corresponded to the decompactification limit with the infinite KK tower, infinite number of KK states. And the second limit corresponded to the safety boundary, actually. And in this case, ground state of 6 BPS states become very light. And you can capture this behavior by computing the Gibbs invariant of this geometry, elliptic P2. So this direction is the T0 charge direction, and this direction is the T1 charge direction. As you see, as you approach it to the boundary, KK state with the same degeneracy whose mass vanishes, and also this string state becomes light. Okay, let's look at the first boundary more carefully. So in this limit, as I explained it, delta 1 vanishes, so it corresponded to 5D shaped fixed point. Then you can compute the metric and see the asymptotic behavior or boundary behavior. Then you see the metric has 0 eigenvalue with the eigenvector 1, -3. And this vector actually denotes the direction in the Coulomb branch where metric vanishes. So gauge coupling diverges. So you can identify the Kahler parameter T tilde for the CFT. And you can rewrite this prepotential in terms of this Kahler parameter for the CFT. And this is the result. And from this prepotential, you can try to identify what CFT we have at the boundary. Okay? So the cubic prepotential is kind of distinguished feature for the given 5D CFT. And actually, if you open the 5D CFT classification, you note that Chern-Simons coefficient or cubic coefficient in front of the Kahler parameter ranges between 1 and 9. And indeed, this coefficient in front of T1 tilde, which now become the Kahler parameter for the CFT, is 9. And we can identify the CFT at the boundary is nothing but the E0 CFT, which actually corresponds to the M theory compacted by the local Calabi-Yau threefold embedding the P2 geometry. Sorry? Yeah, metric positivity on the Coulomb branch. Within the Kahler cone, metric must be positive. There is condition that delta 1 and 2 must be positive or 0. So this condition comes from only after circle compactification. Before that, you don't have this constraint. So this condition is basically for the 5 dispergravity theory. So here we are using it to constrain 6 dispergravity theory, but that condition actually holds for any rank 1 5 dispergravity theory. Okay, let's move on to more complicated examples. So let's consider SU2 gauge theory with no tensor theory, but coupled to the adjoint and fundamental hypermultiplets. So number of fundamental and number of adjoint hypermultiplets are given in this way. And this theory will exist when B is between 1 and 12. And also up to A, we have F theory construction for this theory. However, if B is greater than A, actually this paper tells us that in geometry, we have automatic gauge symmetry enhancement from SU2 to SU2 times U1 mod G2, or SU2 times SU2 mod G2, or SO3 for B equal 9, 10, 11, and 12 cases respectively. Okay? So maybe it's a very interesting question whether the SU2 gauge theory or gauge theory shift supergravity theory having precisely SU2 gauge group with this number of hypermultiplet belong to the Swampland or not. Okay? That is still open question. Sorry? Oh, yeah, yes, precisely. Another point, what do you mean? Yeah, with this metal content, only these are allowed. If you consider other higher spin representations for the SU2 gauge algebra, then you can have more. Yeah. But here I'll consider, for the simplicity, only this model. Okay, we can compute the 5D. We can first compactify to 5D and compute the 5D effective prepotentials. That is this one. Here we use the 3 Kahler parameters. Actually, they are Kahler congelators corresponding to the 3 primitive BPS states. If this theory has geometric realization, primitive states correspond to the Mori congelators. Okay, so QKK means KK charge, and QSU2 corresponded to the SU2 carton charge. Here, QS corresponded to the string numbers. And we have 3 Kahler congelators corresponding to the adjoint hypermultiplet carrying the unique KK charge. And another one is the ground state of a single string. And the remaining one is the fundamental hypermultiplet without carrying any KK charges. Actually, all the perturbative and the simple string charge lattice is generated by these 3 charges of the primitive BPS states. Okay, because this is now rank 2 5D supergravity, and analysis on the Coulomb branch is much more complicated when we have rank 2 theory. So let's first try to reduce to rank 1 theory by Higgsing. Okay? We can consider the following 2 Higgsings. First Higgsing is by giving a valve to just fundamental hypermultiplet. This is a kind of trivial Higgsing where it breaks the SU2 gauge group in 6 dimensions to nothing. So we end up with the Shikti theory with a tensor and vector multiplet compactified on a circle. And as you see, if T2 parameter for this hypermultiplet is sent to 0, then we have this prepotential that agrees with the prepotential for this elliptic P2 model. And second Higgsing is more interesting. So we can give a valve to the Kahler line of the joint hypermultiplet state with this charge. That corresponded to in the prepotential language by sending T0 to 0, then you get this prepotential. Okay? After circle compactification, you can give a valve to the KK state, then you end up with this prepotential. But this prepotential has a negative coefficient if B is greater than 6. But as I explained, the coefficient in the prepotential, when it is written in the Kahler cone, must be non-negative by imposing the positivity of the monopole tensions. So this seems to be problematic, but we know that in geometry, we have construction for the B equals 7 and 8 cases. So what's the problem? Okay, so this doesn't mean that the theory is inconsistent. Yeah. Actually, it simply means the Kahler cone is non-simplicial. It means we can have more than 3 Kahler congelators. So 3 Kahler congelators I explained in the previous slide, but we can have actually more. So the actual Kahler cone is smaller than the cone generated by 3 parameters, T0, 1, and 2. Then what is the origin of the extra Kahler congelators? We can identify such extra Kahler congelators from the extra primitive BPS state coming from the primary field on the 2D CFT on strings. So let me explain in more detail. Sorry? So you have more constraints. So on the Kahler cone, all the Kahler congelators must be positive or 0. So you have more constraints if you have more parameters. That's why it's smaller. Mori cone get bigger because you have more BPS states. And then Kahler cone becomes smaller. And actually, you can trace what is the origin of this extra BPS stage corresponding to the extra Kahler congelators from the world sheet current algebra. So we know that on the world sheet, so we have the string and it coupled to the bulk SU2 gauge symmetry. So on world CFT, we have Bessel-Zimino-Witt model for the that realize the SU2 current algebra at level K, which is now given by Q times B. This level can be extracted from the anomaly inflow mechanism from the 6 dimensions. And we know that this WGW model at this level has a chiral primary field for the conformal weight given in this way. And they can provide, when compactified on a circle, 5D BPS state with the following charge. Here, N corresponds to the KK charge, which actually corresponds to the conformal dimension on the 2D world theory. And L is the SU2 charge, and Q is again string charge. And here, the conformal dimension of the actual chiral primary field on the string world sheet is restricted by Hj from below. Okay. So there is a bound on N. So we can at most identify at this moment only the fact that this WW chiral primary field can provide 5D BPS state of this charge with this bound. But we cannot precisely identify which charge this state can carry. Okay. Only bound is known. And we can use this bound and extract very interesting physics. Before that, let me give you some concrete examples. So you can compute the GV invariant or BPS state counting for B equal A case. So this is a geometric example realized in F theory. So you can use a mirror technique to compute this GV invariant. And this is the result. And here N0, N1, and N2 correspond to charge for the 3 primitive BPS states. So if you look at this point, so its N2 charge is -2. So this arises from a single string. Okay. And actually, this state come from the WGW chiral primary field with L charge -A. So this corresponds to SU2 catan charge. And N equals 3, corresponding to Hj equals so WGW conformal weight 2. And this state cannot be, the charge of this state cannot be obtained from positive linear combination of N0, N1, and N2. So this state provides new extra primitive BPS states. So it provides extra Kahler congelators. And if you write the prepotential in terms of this extra Kahler congelator after circle compactification and fixing, then you can rewrite the prepotential when B equals 7 in this way and B equals 8 in this way. And as you see, all the coefficients, all the Chern-Simons coefficients now become positive. Okay? And they satisfy delta 1 equals 0 conditions. So we have the CFT boundary on the Coulomb branch. And by using the same algorithm I have shown, you can identify the CFT at the boundary where T1 tilde vanishes is E7 CFT. And in this case, we have E1 CFTs. And question was actually, if the theory for B equals 9, 10, 11, which doesn't have the F theory realization unless you admit the symmetry enhancement, can satisfy all the constraints which I presented. And actually, my original plan was to kill these theories by using this constraint, but I failed. So I can say that if there exists some world primary field having small conformal dimensions, these theories could have consistent prepotential. That is at most at this moment I can say. So let me present most interesting case. That is the B equals 12 case. In this case, we have 55 odd joint hypermultiplet. Since we don't have fundamental hypermultiplet, in the messless spectrum, we have G2 one-form symmetry. But we don't know what happens in the massive spectrum. Maybe this one-form symmetry will be broken. And F theory construction is known, and it has only SO3 gauge group. So SO2 gauge group case is not realized in F theory. And you can do the same computation and show that this constraint, delta 1 and delta 2 positive, can be satisfied, after Xing, can be satisfied only if 2D CFT on the 60 BPS string has at least a single chiral primary field with the following charge. In this case, this primary field should agree with the Bess-Zimino-Witten primary field with the following charge for some Q. If a single primary state exists, then this constraint is satisfied. Otherwise, this condition is violated, and this theory will belong to the Swampland. And so, okay, so we can assume, so we first assume such primary state exists, and using the Kahler parameter that provide extra Kahler congelators, using the Kahler parameter T1 for this primary state, we can rewrite the Higgs prepotential like this. So again, all the coefficients are positive, and this prepotential has a delta 2 equals 0 condition. So it means on the boundary where T1 vanishes, we must have the CFT. And you can compute the metric on the Coulomb branch. In particular, at the boundary where T1 vanishes, metric has a 0 eigenvalue with the vector -6 and 1. And this 0 eigenvalue tells us the Kahler parameter for the CFT at the boundary. Then you can read off the cubic coefficient for the CFT at the boundary. And from this computation, the coefficient is 72. But this 72 is far beyond the bound 9 of any known 5D, any classified 5D rank 1 as CFTs. So this means this theory with SU2 gauge theory, gauge group, is inconsistent because it doesn't have a well-defined Higgs branch limit. So Higgsing must be allowed. So this theory in 6 dimensions itself is inconsistent, and it falls into the Swampland. However, here something is weird because there is a F theory realization when the gauge group is SO3, and it seems that we didn't use or we didn't distinguish whether gauge group is SU2 or SO3. But actually, secretly, during this procedure, we assumed gauge group is SU2. Here, T2 denotes the charge of the SU2 cation, and T2 is normalized in this way by assuming that minimal U1 cation charge of the SU2 is 1, and also using the Dirac quantization condition with this assumption. But if the G2 unformed symmetry in the messless spectrum, so the theory has only other joint type of multiplet, so we have G2 unformed symmetry in the messless spectrum. So if we assume this G2 one-form symmetry is promoted to the symmetry of the full theory, and furthermore, if it's gauged, therefore the theory has not SU2 but SO3 gauge group, then actually we have to rescale T2 parameter by half. So assuming that the gauge group is SO3, we can rescale this prepotential in this way. Then we end up with this prepotential, and there is nothing but the prepotential of this strict theory with a vector and tensor multiplet on the circle compactification. So after this rescaling, we obtain the consistent prepotential after Higgsing. Okay. So this proves that strict theory with the 55 order joint type multiplet for the SU2 gauge algebra gauge group can be consistent if the SO3 if the gauge group is SO3, not SU2. Okay. And this also provide very concrete example to show the messless charge sufficiency conjecture. This was conjectured by Morris and Taylor, and this states that messless states generate actually full charge lattice of the gauge group if B for the SU2 gauge or any gauge algebra satisfy these conditions. So this conjecture is very non-trivial conjecture because there are many counterexamples for other cases. For example, 10-dialectic string with the SO32 gauge symmetry has a spinor representation in the massive spectrum. So the spinor states in the massive spectrum, and the spinor representation cannot be formed by the vector representation of the messless field. And also, if this condition is not provided, then this conjecture doesn't hold. But our computation provides very concrete evidence for this conjecture, at least for this example, without using geometry or any string theory consideration. And we perform the same computation for the other rank 1 gauge groups with a tensor multiplet. For example, SU2 gauge theory with integral SU2 spin representations have a G2 one-form symmetry in massless spectrum. These are some examples with a higher B. And we can do the same computation and show that if this G2 one-form symmetry is not gauged, then the theory belongs to the Swampland. And also another interesting example is the infinite family of the U1 gauge theories. So that has 3 different charge hypermultiplet, PR and P plus R. And if P and R has a GCD, non-trivial GCD, then it has a GN one-form symmetry. And for any of these theories, you can do the same computation and show that this GN one-form symmetry in the massless spectrum must be the symmetry of the full theory engaged. Okay. So they provide, again, concrete examples for the massless charge sufficiency conjecture and also no global symmetry conjecture. Okay, let me summarize. So we consider the constraint on the Chern-Simons coefficient on the Coulomb branch of the 5D supergravity theories. And we have studied the Kahler congelators, which can be provided from the primary field on the BPS strings, as well as the shifty massless states. And one-form symmetries of the massless spectrum in 6D supergravity theories with the rank 1 gauge algebra must be promoted to the gauge symmetry of the full theory, which I have shown by doing the concrete computation of the prepotential and also Higgsing and the circle compactifications. You can also consider the following problems, but because of time, let me stop here.